Hello, dear students. Welcome to today's physics lecture. Today we are going to introduce the physical terms work and energy. We are also going to learn that energy of a closed system is conserved. This means that energy does not change over time. What did you do yesterday? Did you work hard? No, you relaxed. So are you full of energy then? Work and energy are terms of everyday language. But in a physics context, work and energy mean totally different things. Let me take you through to the next slide in order to explain the first term. Work. What is work? By work, we mean physical work. It's got a symbol W, W for work, and it's got a unit, joule. If I talk about work in physics, do I mean homework? No, I don't. Or maybe do I mean working hard? No, I don't. But maybe I mean earning money? No, actually not. If I talk about work, I mean that a force is acting on something and it achieves a change in position. So work is when a force has achieved a change in position. Work is defined as the scalar product of the force vector and the displacement vector. So we need a force. The force acts on something and a change in position is initiated by this force. So work is defined as the scalar product of the force vector and the displacement vector. We say work is done by a force on an object. Here you see the definition. Work is the scalar product of a force and the displacement. F is the force vector, R is the displacement vector. We have work, or work is done if a force acts on something and it achieves a displacement. So work is done if the application of a force results in a displacement. Let's look at the units. The unit of work must be given by the units of force and displacement. The unit of force is Newton. The unit of displacement is meter. So, the unit of work is Newton meter. 1 Newton meter equals 1 joule. So, the unit of work is Newton meter or joule. So, here we see the definition again. Work is defined as the scalar product of force and displacement. Work can only be done on a system if the force vector has a component in the direction of the desired displacement. Force and displacement do not necessarily point into the same direction. However, if they do point into the same direction, the angle between the two vectors is zero. Now, the scalar product of two vectors is defined as the magnitudes of these two vectors times the cosine of the angle. Here we see it. Work is the scalar product of the force vector and the displacement vector, which equals the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the two vectors. So if force and displacement point into the same direction, the angle is 0. Now the cosine of 0 is actually 1. So if work is pointing into the same direction as displacement, then work is just given by the magnitudes of force and displacement. It is just given by the product of force and displacement. Now, as the angle between the force and the displacement vector becomes larger, the cosine of this angle becomes smaller. It is 0 for 90 degrees. This is why work can only be done on a system if the force vector has a component in the direction of the desired displacement. So assume force is pointing into the direction as given by the arrow in the picture. Now let's assume the direction of the displacement is pointing into another direction as given by the picture. The angle between the two vectors is alpha. Work is defined as the product of F times cos alpha times R, the displacement. F times cos alpha we find by taking the projection of the F vector onto the displacement vector, as given in the picture now. So the slightly fatter line, as we see it here in the picture, is F times cosine of alpha. F times cosine of alpha is the projection of the force vector onto the displacement vector. So work is given by F times R times cosine of alpha. Let's look at an example for work. A mass point of mass 3 kilograms is pushed by a constant force F equals 30 newtons along a straight line for a total distance of 3 meters. The force points into the direction of the displacement. Let's visualize the problem. Here we've got the force vector. The force vector is given by the magnitude F and an direction. So force vector is given by the direction Ex and the magnitude F. Now let this be the vector of the displacement. R is given by a direction and the magnitude of the displacement S. Now the direction, that is Ex, the direction is pointing into the right direction. To the right, it is pointing to the right as given by the small arrow. That is our unit vector, Ex. So F and R both point into the same direction. They both point into the direction of Ex. The magnitude of the force vector is F and the magnitude of the displacement vector is S. Force and displacement both point into the same direction. Thus, the angle alpha is 0. We remember cosine of 0 is 1. It therefore follows the work W done on the mass point by the force F is given by W equals F times S. It is the product of the magnitudes of force and displacement. Work equals F times X, or work equals F times S. Now F is 30 newtons and S is 3 meters. We know that 30 times 3 equals 90. And Newton times meter equals Newton meter. So work is given by F times S equals 30 newtons times 3 meters equals 90 Newton meters. We also know that Newton meter equals joule. So the answer is a work of 90 joules has been done by the force on the mass point. Let me give you a remark. In this example, it was not necessary to know the mass. However, knowledge of the mass allows us to determine the body's acceleration and speed. Please do that as an exercise at home. Another example. A force of 12 newtons is exerted on a box at an angle of 20 degrees, as shown in the figure. How much work is done by the force on the box as the box moves along the table a distance of 4 meters? Now we see the box, it is here, and it is moving into this direction along the table for 4 meters. Now the force which initiates this movement points slightly upwards at an angle of 20 degrees. So what we need to know is the projection of the force onto the displacement vector. Here we find the projection. And this part here is the magnitude of the force times the cosine of the angle. So if we want to know work, we need to determine the magnitude of the force, which is 12 newtons. We need to know the cosine of the angle here, and we need to know the displacement. So 12 times 4 times cosine of 20 is 4.51. Newton times meter equals Newton meters. So the answer is a work of 4.51 Newton meters or 4.51 joules has been done by the force on the box. Let's look at another example. Here we've got an object of mass 0.5 kilograms. It is lifted up with a constant velocity. Here it is at zero, initially at zero. It is then lifted up to a height of 22 meters. At 22 meters, the object stops and it rests at this height. The question is, how much work has been done on the object by the lifting force? In order to solve this question, we have to determine what is the lifting force. The lifting force, let's call it F lift, is given by minus the weight. Why? Because we need to overcome the gravitation force. So the lifting force is minus the weight. Here we see it. The lifting force, F lift, equals minus the weight Fw. Now Fw is pointing downwards, so it is minus m times g, but minus m times g equals plus m times g, and so it is positive. Now the force points into the direction of the displacement. Thus the angle between the two vectors is 0 and the cosine of 0 is 1. Therefore, work is given by force times displacement. Now the lifting force we can easily calculate. We have been given the mass, 0.5 kilograms, and we know the acceleration. It is minus the Earth's acceleration, 9.8 meters per square second. So this part here is a lifting force. The lifting force needs to be multiplied by the distance. It is 22 meters. Now please get your calculators out. 9.8 times 0.5 times 22 equals 107.8. Let's consider the units. We've got kilogram times meter per square second. That is Newton. And here we've got meter. So the unit is Newton meter or joule. Work can also be understood as the area under the curve. So if we plot the force as a function of the displacement, then work is given as the area under the curve. In the last example, we had a constant force of almost 5 newtons. This force was applied over a distance of 22 meters. So, let's find the force. On this axis, the force is plotted. Here we are, 5 newtons. The force is constant, it doesn't change. It is applied over a distance of, here we see it, 22 meters. The area under the curve is given by the product of the side lengths. So it is distance 22 meters times the force almost 5 newtons. Now if you do the calculation, you should come up with the same result as we had before. Let's look at another example now. Let's consider the work done by a spring. In the picture, you see a spring. The further we pull the spring, the larger the spring force, which makes the spring want to go back to its initial state. If you have pulled a spring in the past, you may have experienced that it becomes harder the more you pull. So if we pull on a spring, there is a force which wants to make the spring go back to its initial state. This force we call spring force. Here you see the spring force. First you can read that F spring, the spring force, is proportional to the distance x. So the further you pull, the larger is x, and the larger is the spring force. Now the constant of proportionality is k. The larger k, the harder it is to pull the spring. Now why is here a minus sign? It is because the spring force is directed into the opposite direction. So pull that way and the spring wants to go back that way. This is the opposite direction. Pull that way and go back. Or push that way. The further you push, the harder it becomes. And the spring force becomes larger. The larger the spring force, the more it wants to go back to zero. So F spring is the spring force. It is the force exerted by a spring on an object at the end of it. X is the extension of the spring. If we pull the spring, or if the spring is extended, X is larger than 0. Or if we push the spring, or if the spring is compressed, X is smaller than 0. K we call the spring constant. Now let's look at the other two pictures. The middle picture here shows the spring at rest. The force is 0 because X is at 0. K times 0 is 0, so no force. But as soon as we pull or push, the force changes. And the force is proportional to the amount of pulling or pushing. Now here in the last picture we see the force. Here it is a force as a function of the extension. So on this axis the force is drawn, and on that axis here we've got the extension. Now here for 0 the force is 0. For 0 extension, as here on that picture, there is no force. And we can see it here by this equation. X equals 0, K times 0 equals 0. So the force is 0. And here you find 0. However, as you push the spring, as you compress the spring, the force increases. It becomes larger and larger. The factor of proportionality is K. The work done by the spring on an object here at the end of it, as the spring goes back to 0, is given by the area under the curve. Can you see? Now let's look at this picture a little bit more closely. We want to know the work. It is the area under the curve. So now it is a little bit different. Before we had a constant force and we just took force times displacement, but now we've got a varying force. The more the spring goes back to 0, the smaller becomes the force. What is the area under the curve? Well, we find the area by integration. What do we need to integrate? We need to integrate the force with respect to the displacement. Now what is the force? It is the spring force. F equals minus kx, remember? Now I need to do the integration between my extension, which in that case is minus x, and 0. So I need to integrate my spring force minus kx between minus x and 0. In order to do so, we need to find the antiderivative. antiderivative of minus k times x is minus a half kx squared. Here you see it. Why? Because if I take the derivative of this entity here, it is 2 times a half, which is 1, minus 1 times kx. So this is the antiderivative of the spring force. Now I need to do the integral between minus x and 0. The integral between minus x and 0 is given by minus a half k 0 squared minus a half k x squared. Minus a half kx squared is just a half kx squared. So the work by the spring force between an extension of x and 0 is given by a half kx squared. It is the area under the curve between minus x and 0. The force is pointing in the direction of the positive x. This is why the work is positive. However, if we've got the work here on that side, if you've pulled the spring to that position here and you want to calculate the work done by releasing the spring and it goes back to here, then you see it is negative. The next term, the next physical quantity I want to talk about is potential energy. Potential energy is stored energy. So if we store energy, we can wait until we want to release this energy. Potential energy is stored energy. It is ready to be released when we need it. How do we store energy? Well, by doing work on a system, we may be able to store energy. If work is done on a system, energy of the same amount may be stored. In the last example, we've done work by lifting the body from 0 to a height of 22 meters. So we've done work on the body and then we've stored this work as energy. It is potential energy, just stored until we are ready to release it. So here's the third example. The body is at a height of 22 meters. Remember, by bringing it up to the height of 22 meters, we've done work on the body. Now, when the body is at a height of 22 meters, potential energy is stored. The potential energy, given as E pot, is defined as m times g times h. H is the height, so it is 22 meters. G is the Earth's acceleration, 9.8 meters per square second, and m is the mass of the body. So this here is the formula for potential energy. E pot equals m times g times h. Now let's put in the numbers of this example. The mass of the body was 0.5 kilograms. G is 9.8 meters per square second and h is 22 meters. Do the calculation. 0.5 times 9.8 times 22 equals 107.8. Kilograms times meter per square second times meter equals joule. Now please look closely. The formula for the potential energy, as given here, is the same as for the lifting work in the last example. Remember how we calculated the lifting work in the last example? We need to consider the lifting force and the displacement. The lifting force was m times g. Here it is. The displacement was h. Here it is. So the formula for the potential energy is the same as for the lifting work. Now, let's visualize it. We've got our body, it is at zero height. Now we lift it to the height of 22 meters. That means we do lift work on the body. The lift work was given by m times g times h. Lift force times displacement. Now this lift work we can now call potential energy, because by doing work we store potential energy in the body, and the potential energy is given by the same formula, m times g times h. Now as long as the body is lying at this height, as long as it rests at a height of 22 meters, potential energy of m times g times h is stored. Now this energy may be released. We release it by dropping the body. If we drop the body from the height of 22 meters, the velocity increases. First it is zero, but then it becomes larger and larger and larger and larger until it's got a maximum velocity at height zero, just when it arrives. Now what I would like you to do is calculate the velocity of the body when it arrives at the bottom. So remember, we had the potential energy. That was the energy of the body when it was resting at a certain height. And now we release the potential energy by letting the body drop. Letting it drop means it starts moving. So potential energy can be released, resulting in a movement. So here's our little picture. The body is up here. Potential energy of m times g times h. Release the energy, let it drop. What is the velocity when it arrives at the bottom? Now whilst the body drops down, the potential energy is transformed into kinetic energy. Kinetic energy is an energy of movement. That's why it's called kinetic energy. So you see the potential energy, which is the potential energy of the body being at a certain height, is transformed into kinetic energy. It is transformed whilst the body drops down. Kinetic energy is an energy of movement. So, in the formula for kinetic energy, as given here, there must be the velocity of the body, because the velocity describes a movement. Kinetic energy is given by a half times mv squared. M is the mass of the body and v is the velocity of the body. So let the body drop, the velocity increases. First at the top the velocity is 0, but it becomes faster and faster and faster and faster and faster until at the bottom the velocity is largest. Now for this particular example here, the velocity at the bottom is given by 2 times h times g and the square root of that. Now that was your task, to calculate it. Because you knew the height of the body, you can also calculate the velocity at the bottom. Now let's put in the numbers here. h 22 meters, g 9.8 meters per square second. Put it in and you arrive at 20.77 meters per second. So the kinetic energy was 0 right there at the top, because the velocity is 0 and a half times m times v squared is 0 if v is 0. However, because the velocity increases as it drops down, kinetic energy also increases until it reaches its maximum value right there at the bottom. Now right there at the bottom, the height is 0. So if we go back and look at the formula for the potential energy, which depends on the height h, we find that for 0 height, the potential energy is 0. So we see that the full potential energy, which the body had got at the height of 22 meters, was transformed into kinetic energy as the body dropped down. The kinetic energy was initially at 0, but then at the bottom it is maximum. But the potential energy at the bottom is 0. So what does this mean? The potential energy is fully transformed into kinetic energy. Every bit of potential energy is transformed into kinetic energy. Now let's look at the numbers. First, we did work by lifting the body from 0 to 22 meters. The formula for the work given by the force and the displacement, F lift times h, and we calculated a value of 107.8 joules. Now we say, if we do work on a body, potential energy is stored. So the potential energy of the body at the height of 22 meters is given by the same formula, and also the numbers are the same here. The work or the energy that we put in by doing work is just the same as the energy that is stored. And now we release the energy by letting the body drop, and the potential energy is transformed into kinetic energy. Now here you see the formula for the kinetic energy. Kinetic energy is given by a half times m times v squared. Let's put in v squared. On one of the earlier slides, I calculated the value for v at the bottom. If I know that the body is dropped from a height h, I know that the square of the velocity is given by 2 times h times g. This is the square of the velocity at the bottom. So, kinetic energy is given by a half times m times the square of the velocity at the bottom. Okay? Now put in the numbers. A half times m is 0.25 kilograms. Now this entity here is nothing but 2 times h times g. which is the velocity squared. And now do the calculation and you come up with a value of 107.8 joules. What do we see? 3 times the same number. Okay? Energy is conserved. It does not change. We do work. By doing work, energy is stored. And we release the energy. And it is transformed into kinetic energy. The numbers are always the same. The energy is fully transformed. No energy is lost and nothing is gained. Now, what we learn by this is that energy is conserved. It means that the total energy does not change. We could also say the amount of energy of a closed system is always the same. It is always the same. It may be transformed from one kind into another, but it is always the same. In our example, we did lifting work and thus stored potential energy of 107.8 joules. Then the body was dropped. The potential energy was fully released. It was fully transformed into kinetic energy. At the bottom, the kinetic energy was also 107.8 joules. So the potential energy at the top matches the kinetic energy at the bottom, because the full amount of potential energy is transformed into kinetic energy. Remember, potential energy is stored energy which can be released. Kinetic energy is energy of movement. So whenever something is moving with a velocity, we can attribute a kinetic energy. Let's have an example for energy conservation. What mass does a blacksmith hammer have, which hits the iron with a speed of 4.5 meters per second and releases an energy of E equals 240 joules? What mass does a blacksmith hammer have, which hits the iron with a speed of 4.5 meters per second and releases an energy of 240 joules? So what's happening here? A blacksmith hammer is a very large, very massive, big hammer. The blacksmith is a person which lifts the hammer to a height above his head and then he lets the hammer drop onto a piece of iron. He wants to shape the iron, maybe into a sword. So he needs to hit the iron with a big, massive hammer. Now the speed of the hammer at the point of hitting is 4.5 meters per second. So we know that something that is moving with a speed does also have energy. It is kinetic energy. Remember the formula for kinetic energy? It is a half times mv squared. V is the velocity or the speed. So as the blacksmith hits the iron with the hammer, there is a kinetic energy given by the speed. and by the mass of the hammer. Mass or half mass times V squared. Now, as the hammer hits the iron, energy is released. It is released in form of heat and deformation energy. So the energy that is released equals 240 joules. Now, if we want to solve that, we need to assume that all the kinetic energy of the hammer is transformed into deformation and heat. Deformation energy and heat. So we assume that energy is conserved. The kinetic energy of the hammer at the point of hitting is given by Ekin equals a half mv squared. The kinetic energy of the hammer at the point of hitting is given by Ekin equals a half mv squared. So now we assume energy is conserved. The full amount of kinetic energy is transformed into the release energy. 240 joules are released, so we can equal 240 joules to the kinetic energy. We know the speed. It is 4.5 meters per second. The only thing that we do not know yet is the mass. So everything is known in this equation here, except the mass. Let's rearrange this equation. And it is given by m equals 2 times Ekin times 1 over v squared. So we assume that energy is fully transformed from kinetic energy to the release energy. So instead of Ekin, we can write 240 joules. 2 times 240 joules equals 480 joules. Now let's time 480 joules by 1 over v squared. Now v squared is 20.25 meters per square second. Yeah. V is 4.5 meters. 4.5 times 4.5 is 20.25. 1 over 20.25 times second square over meter square times 480 joules equals 23.7 kilograms. So the mass of the hammer is 27.3 kilogram. Let's have a summary. What have we learned in today's lecture? We've learned that work is defined as the scalar product of the force vector and the displacement vector, which is given by F times R times cosine of alpha, where F and R are the respective magnitudes of the force and the displacement, and alpha is the angle between the force and the displacement vector. We have also learned that potential energy is given by the formula E pot equals m times g times h. It depends on the height of the object. We have learned that kinetic energy is energy of movement. It is given by the formula Ekin equals a half times m times v squared. We have also learned that energy is conserved, which means that no energy is lost. At any point in time, energy is always the same. Now I'd like to finish this lecture and I thank you for your attendance. Goodbye.